Okay, let's do a little recap on functions and just get used to some terminology as well. The domain and range you would have been familiar with from third year and junior cert level. Codomain you might not. So let's just go through exactly what this is. So functions can be written in any of these three ways, okay? They're all three ways of just listing what a function is. So when we're talking about the domain, we're talking about your x values. In other words, numbers that you are going to input into the function in order to work out a value. So another word for domain are your inputs or your x values, okay? Anything that you're subbing in there into the x, into the function. When you work out what that is, that's what you're going to get for the range. So the range are the outputs, or in other words, of course, what you're going to get for the y values, your results, in other words. And the codomain then, the difference between range and codomain, by the way, it's these two that are linked, not domain and codomain. Range and codomain basically are all the possible outputs, okay? All the possible results, all right? But your range are the actual outputs or results that you get, okay? Codomain are the possible values you could get, but the range are the actual values that you get, okay? So in other words, for the following example where f of x is equal to x squared, if we are stating that the inputs are an element of the natural numbers, in other words, the positive whole numbers, if that's our domain, then the codomain will also be, because it's being squared, a positive whole number. So you're going to have the natural numbers for the codomain as well. They're all the possible outputs. But the actual outputs, so in other words, the actual range will be, if you're taking the positive whole numbers, you're starting 1, 2, 3, 4, inputting them into here, you're going to get 1, 4, 9, 16, and so on, as the actual range that we're talking about. So a little recap on your number systems. Remember, your n are your natural numbers, they're the positive whole numbers. Your z are your integers, they're the positive and negative whole numbers, including 0. Anything that is q, in other words, representing the rational numbers, are numbers that can be written as a fraction. And then or less q is the irrational numbers. So they are numbers that cannot be written as a fraction. So for example, pi or roots of prime numbers would e, for example, they are all irrational numbers. They would be never-ending decimals that take no recurring pattern and therefore cannot be written as a fraction. Okay, another important aspect is figuring out whether or not something is actually a mathematical function. So the key thing to remember here is, for it to be a function, one input cannot produce two outputs, okay? Because if that happens, it is not a function, okay? So one input can not ever produce two or more outputs. So if you have something graphically drawn for you, we can do what's called a vertical line test for a function. If you draw a vertical line anywhere on the graph, it can only cut at most once, okay? That would mean that one input can produce just one output. If the input was here, it would produce an output there. If the input is here, it produces the output right there on the curve. If it have an input here, it produces an output up here somewhere. So you can only, through a vertical line test, have that cut once. Over here, for example, though, where they have the vertical line drawn here, that input produces this output here and an output down here. And we cannot have that. One input cannot produce two outputs. So a vertical line test, where you put that vertical line anywhere on the graph and you see that it cuts more than once, you know that that therefore is not a function. So this one is a function, but this one is not what we would call a function. So remember the fact that one input cannot produce two outputs. If we're talking about a mathematical function, if you've got something drawn for you, you can use the vertical line test. In other words, draw a vertical line anywhere on the graph, and if it intersects the graph more than once, it is not a function. And just if you have a mapping diagram, so if you have a mapping diagram here where you have the inputs or the domain -2, 2, 3, your function is f of x equals x squared. In other words, you're squaring the numbers. You can have two inputs that will map to the same output. That's okay, because -2 all to be squared will give you 4, and 2 all to be squared will give you 4. This, though, over here is not okay. This is where, look, you have one input producing two outputs, and that, of course, we cannot have if we're talking about a function. This one's fine, but this one input going to two outputs, is not a function. Okay, so I want to talk about composite functions now. So if you have f of x is equal to x plus 3 and g of x is equal to x squared minus 1, then we are going to answer the following questions. We're going to find f of g of 2, g of f of minus 1, and f of g of x. Okay, so if you have an idea what you might do here, press pause and see how you get on. Otherwise, I'm going to explain it more thoroughly now. So with composite functions, what you're going to do is you're going to work with the two functions at the same time, and you'll always read backwards. So what we're going to do is we're going to put the 2 first into the g function, and then we're going to put that, whatever we get for that, into the f function. Okay, that's how we're going to do this. So let's take, first of all, g of 2. And if we want to figure out g of 2, since g of x is equal to x squared minus 1, g of 2 is going to be when we sub in 2 for the x. So we get 2 squared minus 1, which is, of course, 4 minus 1, which is 3. So g of 2 is equal to 3. We're going to take that 3 now, which is what g of 2 is, and sub it into the f function. So the f function, or f of x, is x plus 3. So now I want to take my result for g of 2 and sub it into that f function. So I get 3 plus 3, which is 6. So 6 is the answer there to part I. Okay, so take a look at part 2. So part 2 is g of f of minus 1. So this time we're going to put minus 1 into the f function and then put that result into the g function. Okay, so we'll first of all look at f of minus 1, and then whatever that is, we'll put that into the function g. So f of minus 1, well, if f of x, of course, is x plus 3, then f of minus 1 is going to be minus 1 plus 3, which is 2. So now I'm going to put that f of minus 1 into the g function. In other words, 2 is going to go into the g function. So the g of x function is x squared minus 1. So now g of 2, which is what f of minus 1 is, will be 2 squared minus 1, which is 3. So that's the answer for g of 2. And so the last part is f of g of x. So we're going to basically, we don't have a number here, but we're going to take the g of x function and sub it into the f function. So g of x is equal to x squared minus 1. So we're going to take that and sub it into the f of x function, which is x plus 3. So that means we're going to sub that into there. So instead of f of x, we're going to have f of x squared minus 1, which means instead of the x here, I'm going to sub in x squared minus 1. So I end up with x squared minus 1 plus 3, which is equal to x squared plus 2. So the types of functions we deal with, we have linear functions, which of course represent a straight line. And if you were to asked to graph the function, let's say the function as given here, 2x minus 4, you can just see where it cuts the x and y axis. And of course, if it cuts the y axis, you let x equals 0, get the corresponding y coordinate. So it cuts the y axis at minus 4. And if it cuts the x axis, you let y equals 0. And you get 2x minus 4 equals 0, so therefore x is equal to 2. So it cuts the x-axis at 2. So linear functions represent a straight line. Then of course we have quadratic functions. They would be of the form ax squared plus bx plus c. And if the number before the x squared is positive, it of course will be a U shape, and if it's negative it will be an N shape. With a quadratic, a power of 2, you will always have one turning point. And if the number before the x squared is positive, you will always end tail up. If the number before the x squared is negative, you will always end tail down. Power of 2, one turning point. Okay, so here you'd have a minimum point, and here you would have a maximum point. So in order to find your turning point or your maximum or minimum point, you can use calculus and differentiate, put it equal to 0 and solve. Or of course, if you get your quadratic and complete the square, get it in that form, then from that form you can pull out what would be the maximum and minimum point. Okay? And then of course we have cubics that would take the form ax cubed plus bx squared plus cx plus d. So the graph of a cubic function will either look like this or like this. And again, it depends on your coefficient this time of the x cubed. Since it's a power of 3, you will have 2 turning points. And if the coefficient of that power of 3 is positive, it will end tail up. If it's negative, it will end tail down. All right? So following on that pattern, if you did have polynomials of degree 4, in other words, that you had a power of x that is 4, then what you would expect to see with the graph of the function is 3 turning points. If the coefficient of the x to the power of 4 is positive, it will have 3 turning points ending tail up. And if it's negative, you will have 3 turning points ending tail down. And so on and so forth, as it would continue on then with polynomials of degree 5, of degree 6, and so on. That's what you would expect to see in the most general form. So with regard to finding the functions, if you have a linear function and basically you want to find the equation of the line, then of course the equation of the line, we would follow the formula in our log tables. Y minus y1 equals m times x minus x1, and for that you need a point or a slope. Or of course you can use y equals mx plus c if you know what the slope is, or you can spot what that is from the graph and you know where it cuts the y-axis. That is what your c always is, where it cuts the y-axis. So if then you are looking for the function of a quadratic, well, one of the things that's very useful for us to know is of course that every quadratic will take the form of x squared minus the sum of the roots times x plus the product of the roots equals 0. So you can add the roots together and change and make sure it's a minus. That is the coefficient of the x, and the product of the roots, in other words, when you multiply the roots together, then that will be the number, the constant at the end. So then of course we also have the other bits of information from our completed the square form, because obviously if you have it that you know maybe what the minimum or maximum point is, that also can tell you some valuable information about the actual function. So if we're putting it in the completed square form, that's what the completed square form would look like, of course. This would give you a positive U shape because we would have a positive x squared. And when it's written in that form, of course, it's the p and the q is the minimum point. So if you have the p and the q, that's what you can sub in here for the minimum point. Then of course you have, if it is an N shape, and therefore you end up with something like this when you have the completed square form, it's going to have PQ as the maximum point, and so if you can see the maximum point, that's where you can sub it in order to find out more information about the actual quadratic function. Okay, so with cubic equations, if we jump straight into this example here, say you're trying to get the cubic function from this graph, then again your roots are what's going to give us a huge amount of information here. So it cuts the x-axis, we can see, at -2, 0 and 2. And so since we have x equals -2, 0 and 2, that tells us then that if you have x equals 0, x equals -2 and x equals 2, Then before that, you would have had this. Before that, you would have had this, in which case this obviously was in the factorization, or they are factors of it. And if it's x equals 0, then of course you would just have an x there, and that has to make up part of the function. And then of course you could multiply it all out. The problem is though, you could have had, say for example, a 3 here, and you'd still get 3x is equal to 0, x is equal to 0, okay? Or a 4, or a 5, or something. So the problem is we're going to have to cater for the fact that we don't know whether or not there is a multiplier in front of this factor here. So we'll have to consider there to be some value, we'll call it k times x plus 2 times x minus 2, definitely, that's how we're getting these and these roots. But we may have a number here before that x, so the function is of this form, and now we've got to figure out what that k is. So in order to do that, we've got to look to the graph to get some more information, and any point on the graph is going to give us enough information here. So we can quite clearly see that it goes through the point 1, 1. So now you have your form y equals kx, we have some number there possibly, times x, then we have x plus 2 and x minus 2 to get the roots minus 2 and 2. So what we do then is we use the fact that if x is 1, the function must result in 1, the input is 1, the output is 1, or the x value is 1, the y value is 1. Putting 1 in for y and 1 in for x, we get the following, and we can solve for k. And we do have a value for k here. K is working out to be minus 1/3. So therefore the equation of the function is this. So another type of graph you need to be familiar with are exponential graphs, okay? And exponential graphs take the form of a to the power of x. And we're just going to look at when a is greater than 1 for the moment, okay? So there are some typical examples over here. If you have y equals 2 to the power of x. So exponential, as I said, is when you have a power of x, okay? If you have y equals 3 to the power of x, the blue curve is this one here, and y equals 4 to the power of x is the black curve here. You can see that as that number a increases, the curve gets steeper. But something that they all do is they all cut the y-axis here at 0, 1. And the reason for that is, if I take the example y equals 2 to the power of x, well, when x is equal to 0, y is equal to 2 to the power of 0, which of course, anything to the power of 0 is always 1. And that's why we're going to get 0, 1 there. Always, for anything that you're putting in a power of 0. So that's an important part on these exponential functions. The other important thing to note is the x-axis is always an asymptote. Now, what that means is the curve will approach and get closer and closer and closer to the x-axis, but will never cross it. Okay, that's what an asymptote is. It's a line which the curve approaches but never touches. So what does that mean? That means, take the example y equals 2 to the power of x again. That means this value here will never be 0 or below. Okay, so let's consider that for a moment. That means 2 to the power of something will never equal a 0 result, because if it did, it would cut the x-axis, and it will never equal a number below 0, or it would go through the x-axis and be down here in the negatives on the y. So, for example, we've already seen that powers of 2 to the power of 1 is 2, 2 to the power of 2 is 4, 2 to the power of 3, and so on. It's just going to get higher and higher. 2 to the power of 0, we already know, is 1. Even if we consider x values which are negative, 2 to the minus 1, of course, is the same as 1 over 2 to the power of 1, which is a half. And 2 to the power of minus 2 is equal to 1 over 2 to the power of 2, which is a quarter. And so even if you're subbing in negative values for the x, you're going to end up with fractions. And so that number will get smaller and smaller and smaller and smaller and smaller naturally, but it will never end up to be 0. No matter what I sub in here for the values for x, it will never give a 0 result, and you'll never get a negative result. So the x-axis is an asymptote. The curve always approaches it, gets closer and closer and closer and closer. As it gets smaller and smaller and smaller and smaller, those values, it will get smaller and closer to the x-axis, but it will never, ever cut it. So the other thing we just need to consider is when we have an a value that is between 0 and 1. The ones we looked at before were all greater than 1. But if you have a value for a that is between 0 and 1, in other words, you have a fraction, then what are we going to get? So here's a typical example of where we have the a value is a half to the power of x, of course, which is what makes it an exponential graph. The power is x. So when you sub in your different values, you can see the effect that it's going to have. You see, a half to the power of x, of course, can be written as 2 to the power of minus x. So I'm just going to write that out again here. Y equals a half to the power of x is the very same as 2 to the power of minus x. Because, of course, if you remember, when you have a power that's negative, it's the same as 1 over, and then you still have 2 to the power of x, so 2 to the power of x, and that, of course, is the same as 1 to the power of x over 2 to the power of x, because 1 to the power of anything is still 1, and that's why we can write it then as 1 over 2 all to the power of x. So when you see what's happening here, so you have 2 to the minus values, I suppose, you're going to have then the exponential function going the other way. The x-axis is still an asymptote. You're still cutting at 0, 1. Okay, when x is 0, the y is still going to be 1, but the graph is going in the other direction now. And so to recap then, your exponential graphs, so a to the power of x when a is greater than 1 will look like this shape, and a to the power of x when the a is between 0 and 1, in other words a fraction, you will have this shape. So then we need to look at logarithmic functions. Now there's a specific relationship between the logarithmic function and the exponential function, and you can see that quite clearly with this example. So a typical exponential function would be y equals 10 to the power of x. The logarithmic function, log of x in the base 10, is that function reflected in the line y equals x. It's what's called an inverse function to 10 to the power of x, and I'll talk in a little bit more detail about inverse functions and how to actually find them, but the log function is an inverse function of the exponential functions, and what that looks like is it is a reflection of that graph in the line y equals x. So where the exponential function cut at 0, 1, all logarithm functions will cut at 1, 0. Okay, and where with the exponential function the x-axis was an asymptote, in the logarithmic functions the y-axis is an asymptote. Okay, so that is the relationship between those two. And so the exponential function y equals e to the power of x has the inverse function then y equals ln to the power of x, in other words log in the base e. And so again, to point out, the graphs are reflections of each other in the line y equals x. E to the x, the exponential function e to the x, has the x-axis as an asymptote. Ln x has the y-axis as an asymptote. For y equals e to the x, you are only going to get positive values. Okay. For y equals ln x, you do not have any values for when x is negative. Okay, so the range is always the real numbers. You can have negative values for the outputs, but you can't have any negative values for the inputs for log in the base e. E to the power of x is positive for all values of x, but ln x does not exist therefore for negative values of x. So there are the important points about the functions e to the x and ln x, in other words log x in the base e.